Welcome back. So in previous videos, we started to talk about three-dimensional structure, right? So we have tetrahedral carbons, and we looked at Newman projections and said sometimes the groups are oriented this way, sometimes they're going to be oriented this way, opposite each other, all of these kinds of things. And so this kind of introduced the idea that organic molecules have three-dimensional structure. So the next unit that we're going to talk about, and we're going to start to talk about stereochemistry, which is all about three-dimensional structure of organic molecules and what happens when we have these sp3 tetrahedral carbons and this means something different than this, right? If this group is fluorine or whatever, if it's pointed if it's pointed towards you, if the fluorine is pointed towards you, that's different than if the fluorine is pointed away from you. And the Newman projections will help us say when it's more stable for that fluorine to be pointed one way or the other, but we can also make molecules that look different depending on that. Okay, so we're going to define some terms in this video, and then we'll do some examples in future videos, so you'll see all that fun stuff. So this is a lot of definitions, so lots of writing and lots of words on these slides. Okay, so the first definition we're going to do is stereoisomer. So a stereoisomer is or stereoisomers, I should say, are compounds that differ based on orientation in space, right? Which is a long, fancy way of saying their 3D structure. Okay. So there are going to be two types of stereoisomers that we're going to talk about. So stereoisomers is kind of the big umbrella term that encompasses everything. We're going to have two types of stereoisomers that we're going to talk about. The first one is enantiomers. Enantiomers are stereoisomers that are mirror images of each other. That are mirror images of each other. So enantiomers always come in pairs, right? There's a right-handed version and a left-handed version. So this is where I always say, have you ever really looked at your hand? Like, you really looked at your hands? If you look at your right hand and your left hand, I'm probably switched, so I do know my right from my left, I promise. But if you look at your two hands, right, if you try to lay your right hand on top of your left hand, you can't do it, right? My thumbs go the wrong way, my pinkies are on opposite sides, right? All that kind of stuff. The only way I can get my fingers to line up is if I mix up my palm and the back of my hand. If I do it this way, right, then my palms and my palms are oriented different directions, and then I get my fingers to line up, but my palms don't line up and the back of my hands don't line up, and so I can't overlay my two hands exactly correctly. Organic molecules, when they have three-dimensional structure, are much the same way, and so we have right-handed organic molecules and we have left-handed organic molecules, and your hands are also mirror images of each other, right? If you imagine there's a mirror right here, if I hold, well, we're actually doing this. If I hold my right hand up to a mirror, which is what I'm doing, it looks like my left hand, right? So to you, it looks like I'm holding up my left hand, I think, if I've got this whole webcam thing figured out. But I'm holding up my right hand. And so my right hand, the mirror image of my right hand is my left hand. So my hands are enantiomers of each other, right? Or they would be if I hadn't have broken my finger, and they're no longer even close to identical. And that's not the point, right? So, but the idea is when we think about enantiomers, they're always going to be pairs. They're always going to be kind of mirror images of each other, right? So now, what is the other option? The other option is if they're not enantiomers, they are diastereomers. And diastereomers are basically stereoisomers that are not mirror images. So diastereomers are kind of the catch-all that catches everything that's not an enantiomer. So we're going to define what an enantiomer is, how to find enantiomers, and then we're going to look at what are other stereoisomers and what do they look like. And kind of across the board, they're all diastereomers. Right? So we're going to start with enantiomers because that's the one that actually has a whole definition. Right? So we look for sp3 carbons with 4 different groups attached. Right. So let's do an example. Let's look at, we're going to look at methylhexane. 1, 2, 3, 4, 5, 6, and I'm going to put a methyl group down here, and I'm going to make this methyl group wedged. So this methyl group is coming out of the screen at you. The hydrogen is going back into the screen away from you. Right? This carbon right here, the one that I'm going to mark with a star, is exactly this. It is an sp3 carbon, right? There's no pi bonds here, and it has 4 different groups attached to it, right? So we can list those groups, right? We have a hydrogen, we have a methyl group. So this is one group. Whoops, that's bad circling. This is group number 2. Here's group number 3 that's attached to this carbon, right? It's a 2-carbon chain. So our group number 3 is CH2, CH3. And then our 4th group is a 3-carbon chain. CH2, CH2, CH3. And so at that starred position, we have 4 different groups attached to each other, or attached to that sp3 carbon. This satisfies the definition for what we're going to call a stereocenter, or a chirality center. You'll see these used. Some people say that these mean different things. Those people are crazy. Mostly, in 99% of the cases, these are going to mean the same thing. Right? So a stereocenter or a chirality center is defined as an sp3 carbon with 4 different groups attached. Why is this important? The big important rule of stereoisomers is that any compounds with stereocenters are chiral, which is why they're sometimes called chirality centers. And all that chiral means is meaning they have a mirror image. Right? All right, sorry, I shouldn't say mirror image, because everything has a mirror image, right? You hold anything up to a mirror, assuming it's not a vampire, and it'll have a mirror image. Not only do they have a mirror image, but the mirror image is different, right? So a stereoisomer is a compound that's different based on orientation and space, and enantiomers are stereoisomers that have mirror images that are stereoisomers. So that means that they have an enantiomer. Right? So a compound that has a stereocenter, an sp3 carbon with 4 different groups attached to it, a compound that has a stereocenter is going to have an enantiomer. So of course the question is, what does that enantiomer look like? How do we draw that? How do we deal with that? And so I'm going to do that, and that will probably finish off this slide. So I'm going to go back to 3-methylhexane here. I'm going to draw it the same way that I drew it on the previous slide. CH3 coming at you. Hydrogen going away, 3 more carbons, right? So we've already established that there's a stereocenter right here. It's an sp3 carbon. It's got 4 different groups attached to it. If we draw the mirror image, so pretend that this is a mirror, right? If we draw the reflection of this molecule through that mirror, right? So this carbon, this CH3 group right here, is the closest one to the mirror. So on the other side, that would reflect here. And then as we move away from the mirror, we do the same thing in the reflection. This methyl group is going to be reflected over here, CH3, and the hydrogen is going to be reflected there. And so this is the mirror image. We've drawn the mirror image of this compound. So here's our original, and here's our mirror image. So now if everything I told you on the previous slide is true, we have a stereocenter, so that means that we should have an enantiomer, which is a mirror image that is a different compound than what we started. So this is called a non-superposable mirror image. And that's what we have here, right? If we pick this molecule up, and so here's our stereocenter, right? If we pick this molecule up and put it on top of the molecule over here, we can get the methyl group and the hydrogen to line up with each other, right? This methyl group can overlay with that one exactly in the hydrogen, except that in this case, we have the 3 carbons going off to this side, whereas on our original structure, we have the 3 carbons going the other direction. Right? So if we laid this one on top of that one, if we just picked it up and put it on top, the 3 carbon chain would be on the wrong side and the 2 carbon chain would be on the wrong side, and these two wouldn't overlap. Right? This is a lot like the example of our hands, right? If I lay these on top of each other, the thumbs end up on opposite sides, right? And of course, if we flip it over so that we line up the thumbs, then we're changing what's toward you and what's away from you. Right, so think of my thumbs in this case are the kind of the 2 carbon chain or the 3 carbon chain, right? If I put the mirror right down the middle of my body, right? The thumbs, these are mirror images of each other, and if I lay one on top of each other, they don't line up because the thumbs are pointing in other directions, opposite directions, right? If I flip it over, now the thumbs line up, but now what's toward you and what's away from you are different, right? And so in this case, right, imagine that the stuff that you can see is the wedged groups, and the stuff that's on the others that I can see on the other side of my hands is the dashed groups, right? The things that are pointed away from you. We can line up the other groups, but we can't line up the wedges and the dashes in that case, right? So, oh, I'm gonna push the wrong button here. Yeah, so in this case, if we try to flip this over, right? If we take this mirror image and flip it over, we flip the mirror image, oops. Right, what we'll get is we'll get the 2 carbon chain on this side, the 3 carbon chain over here. Here's our stereo center, our chirality center. But what we've done is we've flipped what's toward us. Nope, that's not what I want to do. And what's away from us. So now the methyl group is back and the hydrogen is up. And so when we put this on top of our original structure, the methyl group and the hydrogen won't line up. And so what we have non-superposable mirror images. Therefore, these 2 structures, right, this one and this one, are enantiomers of each other. Okay, so the big rule, the big take-home message from this first video is enantiomers. Whoops! Oh my gosh! Pardon my handwriting. Enantiomers come from the mirror image of a compound with stereocenters. Well, we'll say a stereocenter. We'll deal with multiple stereocenters in a future video. Right? So enantiomers come from the mirror image of a compound with a stereocenter. That's how we know what is and is not an enantiomer. There are other ways to kind of find enantiomers and stuff. We'll talk about them in future videos, but for now, that's a nice first definition. So stick around. We're going to go into what do diastereomers look like? What happens if we have multiple stereocenters? And what are the exceptions to these rules? Because, of course, there's always got to be an exception. So look at those videos coming up next, and I'll see you soon.